All right, welcome. Welcome everybody. My name is Tal Eisner. I'm the Global Marketing Manager for CPR. Those of you who do not know enough about CPR, which I'm sure you do, CPR is the intelligence arm of Checkpoint Software. This is a group of over 150 people, researchers, that are doing different ways, in different researchers in different groups. Some of them dealing with product vulnerabilities and technology vulnerabilities through attacks of interstate attacks. And this is a group that is very committed to the general benefits of the global intelligence community, and of course the safety and a secure product for Checkpoint customers. We have a great 2 days, today and tomorrow, of this breakout session, which is called Hackers Exposed, or here is the, exactly, this is what I meant, and thank you. So we have enormous 2 days with great sessions of our best researchers with the top stories that we researched over the past year, and we invite you all to come today and tomorrow. Also remind you that you have on your seat an invitation to join our podcast channel, the new podcast channel that we've just launched that goes by the name of CP Radio. You can find it in any one of the channels, Spotify, Apple, Google, or whatever podcast channel you're using. Please subscribe us to get the latest of our podcast. We're going to start today our session with a session called Hijacking a Botnet. Shocking news about botnets often appears in the media, but do you really know how botnets are researched? With what you're going to hear here from my friend Alexey, you will learn how to reveal a botnet consisting of million bots and how malware creators protect their bots from hijacking. We will disclose a weakness in the authentication protocol of a well-known botnet that makes it possible to take control over infected computers and take down the botnet. Please give a round of applause for Alexey. Alexey is a malware reverse engineer in Checkpoint. He specializes in malware research automation, Windows kernel mode development, macOS emulation, and for the past 2 years, he has been fascinated by research of botnets. Please accept Alexey.
Okay. So, a botnet is a network of malware-infected computers that can be controlled remotely, forcing them to execute commands without the consent of computer's owners. To control infected computers, cybercriminals often use command and control servers, or CNC. There are also peer-to-peer botnets that are controlled without a CNC server, but we won't consider them in this talk. What did we want to achieve in this research? First of all, we wanted to understand how botnets work. I'll describe the communication protocol and some tricks used by a real botnet. Next, we wanted to find common steps in researching botnets. We'll show services and software that we use for researching malware and botnets. Next, infiltrate a botnet and get relevant indicators that help us to create protections against it in our products. And our final goal, try to take control of our bots. Our target today is Remnant botnet. What do you know about it? It's really old, but it's still active. It has currently more than 100,000 computers infected, but it is known for infecting more than 1 million computers in previous years. This malware has modular architecture and a lot of functions, and actually it gives almost full remote control over infected computers. So what to start with? How to start the research? Initial data sources on the malware could be darknet forums, malware research reports, and publications, including our publications. Technical reports usually include a section which may contain hashes of samples analyzed by researchers. Using that hashes, we can download malware samples from VirusTotal service and start our research. Malware is usually created to be configurable. This implies using different encryption keys, sets of command and control servers, and file names in various samples. And Remnant malware is no exception. It has a section storing configuration which could vary in different samples. Now we are interested in the following values that are stored in the configuration: encrypted domain names and a DJ seed. These values are used for locating command and control servers. And what is DJ here? DJ stands for Domain Generation Algorithm. It is a function similar to a pseudo-random generator and usually has 3 inputs: the current date, the seed value, and the counter. DJ output domain names can be predicted because the initial state of the generator, the seed, is known. It is stored in the malware configuration. We extracted the DJ from a remnant sample, and it is very simple, as you can see here, and also it doesn't depend on the date value. When I dealt with the botnets for the first time, I researched only a few samples, and after creating a small script that re-implements DJ with the extracted seed, I was surprised that it was unable to find the active CNC server. So what was wrong? Obviously, the CNC server for this configuration was offline at that moment. This could be for several reasons, but it was extremely important for me to get an example of malware communication to continue my research. But is it possible to obtain CNC traffic without communicating to a real CNC server? Fortunately, there are such services as VirusTotal and RiskIQ Passive Total that could really help. RiskIQ Passive Total provides access to passive DNS resolution data. It contains snapshots of DNS requests and IP responses from DNS servers in different periods of time. Using RiskIQ, we can get this data even when domain name doesn't exist anymore. If we search one of CNC domains from known remnant configuration, we can see the IP address to which the domain was being resolved at a certain date. VirusTotal stores data collected during emulation of a sample in several sandboxes. VirusTotal allows us to search through this data. We can find a sample by IP address that it accessed during the emulation. In our case, we found 3 samples, as you can see. The analysis report may contain PCAP file with a recording of a sample's communication. We can download this file by clicking PCAP button. And we have got a real CNC traffic even without running a sample. Actually, it requires a lot of reverse engineering work to understand the communication protocol, but communication examples really help. So, Remnant implements its own binary protocol over TCP. Every message between a bot and a CNC server starts with a header that contains magic word 00FF and message length. The message data follows then. Message data has mandatory field code and optional chunks. The number of chunks depends on the message code. Here are the examples of codes and their meanings. It's a check-in request, verify server, upload screenshots, upload cookies, and get comments. A chunk can be one of 3 types: chunks of fixed size of 4 and 8 bytes, and a chunk of variable size for transmitting arrays. For this type of chunk, RC4 encryption is used. The encryption key is stored in the malware configuration. Let's now look at the example of communication between a bot and a server. Message starts with a magic word 00FF, and then message length follows, message code, a chunk type, length of the chunk, and the chunk data. This is a check-in message from which every communication starts. The server answers with the message 01 OK if everything is OK. The bots then request server verification, and the server answers with some long array. Let's take a look inside the last message. It contains of 120 bytes length array. If we decrypt it with RC4 and then encrypt with RSA, using the case from the malware configuration, we can get the ASIN1 sequence containing 20 byte string, which is actually SHA1 hash of CNC server's IP address. And you've just seen a hijacking protection mechanism of Remnant botnet. How does it work? Bot has RSA public key in its configuration, and CNC server has the corresponding private key. It issues signature of its IP address and sends to this bot. Bot decrypts the signature using its public key and compares with the SHA1 hash of CNC server's IP address. If the values are equal, bot continues communication. If a server doesn't know the private key, it can't issue a valid signature for its IP address, and the bot stops communication with such a CNC server. What is good in this verification protocol? Only a CNC server which knows RSA private key can issue a valid signature for its IP address. But what is bad? RSA signature has only one argument, IP address of a CNC server. So a valid RSA signature can be reused. This is a real weakness that allows us to take control of our bots. Let's assume that we are running a fake CNC server. We can collect a valid RSA signature of a real CNC server. And then when CNC server moves to another IP or goes offline, we can acquire its previous IP address for which we have already collected the valid RSA signature. And when bot connects to our server, we can pass the verification even without having the private key because we have the RSA signature for our IP address. But you may ask me how to acquire the IP address of a real CNC server. In valuable number of cases, the Remnant actors use cheap public VPS hostings that manage small IP subnetworks. When the required IP address is free, we can purchase VPN hosting service at the same provider and register new VPS instances until we get the required IP address. Or get any IP address within the subnetwork which contains the required IP address and run ARP spoofing attack on the gateway to obtain the required IP address. You might be surprised, but some of small VPS hosting providers are still vulnerable to ARP spoofing attack. When we found several configuration variants of the malware, we must ask ourselves, is it a complete set of configurations? Because to control the botnet, but not only a part of it, we need to get all possible malware configurations. And this is a reason to obtain as many samples as possible. But where can we get more samples? Very often malware use specific patterns or algorithms for naming files, directories, and other objects. Remnant uses deterministic pseudo-random generator for generating mutex names. It depends on system volume serial number of the infected computer. And if we search in VirusTotal for a known sample by its hash, we can find the mutex name in the emulation report. And for all emulations in the same virtual machine or cloned from the same image, the mutex name also will be the same. So we can use this mutex name in a VirusTotal search query, and this gave us amazing result. We found more than 13,000 samples, and now we have a lot of samples really. So it's time to implement our fast configuration extractor. The configuration is stored in the data section and can be located by specific signatures. We implemented an IDA script for configuration extraction. The script locates configuration, then it extracts configuration values by static offsets that we determined manually. Finally, it decrypts string values such as campaign name and CNC domain names. This script is a very good enhancement that allows us to extract configuration almost automatically in a few minutes. However, this approach has several disadvantages. The thing is that the most of samples come packed or encrypted. Configuration extractor obviously fails on such samples. Using extractor in IDA also requires a lot of manual work, and it's absolutely impossible to process big number of samples using such approach. So we need a solution that automates the entire process. Packing and encryption helps malware creators to circumvent static detection of the malware and to complicate the research process. One sample can be packed and encrypted with different methods using different keys, therefore every packed sample is unique. There are hundreds of different packers. We can spend a lot of time to create unpacker for some case, but not for all of them. Therefore, configuration can be extracted statically from all packed samples. However, we can run the malware in a sandbox. To perform its malicious activity, the sample unpacks itself. The sandbox must track all processes that malware affects and create memory dumps. Created dumps may contain unpacked code and data. In our lab, the dumps are passed to Yara, a tool used in malware research. It provides a rule-based approach for malware detection based on textual and binary patterns. On a Yara rule hit, a configuration extractor for the corresponding malware family is invoked. On the left, you see the example of Yara rule for one of Remnant malware variants. The rule hits on a condition when a dump contains a specific text string and a binary sequence. Configuration extractor is very similar to the IDA script that we discussed before and deals with offsets in configuration. Cuckoo Sandbox provides a framework for creating such laboratory. We just need to adjust creation of memory dumps, write Yara rules, and implement configuration extractors. There is also a product Cape Sandbox based on Cuckoo. In Cape, all this stuff is already implemented for some of malware families, for example, TrickBot and Emotet. Also, they are very known. We created our lab on the basis of Cuckoo Sandbox. With our enhancement on the report summary page, you can see the name of the detected malware family and the important parts of its configuration, such as URLs of command and control servers. By clicking extracted artifacts, you can view the entire extracted configuration. Also, we can view the list of all emulated samples. The list contains MD5 hashes of emulated samples, detected malware family name, and extracted configuration type. Also, let's pay attention to these two rows. Each of them contains more than one malware family name, and this is not a mistake. Some packers are able to create bundles from 2 or more different samples. This allows cybercriminals to deliver more than one piece of malware at the same time. I even saw 2 versions of Remnant bundled in one sample, and this is really confusing, but our laboratory handles such cases correctly. We can view configuration of each sample packed in a bundle. Finally, to collect all malware configurations, we need to set up constant delivery of malicious samples. This also can be done with the help of VirusTotal and its API. So the results of our IC configuration, IC extraction laboratory. Within 6 months, we processed more than 50,000 samples, and we managed to extract 97 DJ seeds and more than 6,000 domain names generated from these seeds. As you can see, there is a wide variety of malware configurations. It's a good idea now to classify them. We found samples with 3 different RC4 keys used for communication encryption. And also we found a set of very old malware variants that don't use encryption at all. For each RC4 key, up to 5 RSA keys were found. These 3 groups of bots are likely controlled by different cyber criminals. A part of bots don't have RSA key because they don't perform CNC server verifications. Botmasters also give a name for every campaign, and we found more than 100 campaigns. Let's pay attention to this part of the picture. Really no CNC verification. This means that bots can be controlled by anyone who owns domains from malware configuration. Fortunately, almost all of them are already taken by malware researchers, including us. And we now have a very good visibility of the botnet, even without contacting a CNC server. It's really great. But what can we do after infiltrating the botnet? Infiltrating the botnet implies creation of a fake bot which connects to a CNC server and makes it to think that a real bot has connected. Such a bot can receive commands from CNC server, download malicious payloads and other data that can help to create protections against this malware. Let's try to get something interesting from the CNC server. First important thing that we can get is RSA signature for server's IP address. We have collected the signatures for 42 IP addresses and for 5 different RSA public keys. We can also assess the botnet prevalence. At a certain stage of communication, a bot sends information about infected computer to a CNC server. The data to be sent includes MD5 hash of a unique identifier of the infected computer. The response from a server contains a number which grows by 1 if we change MD5 hash and stays the same if we send the same hash. We just need to generate a new MD5 hash and the CNC server will send us approximate quantity of currently infected computers. This is the same message converted to JSON format for convenience. You see the number of bots of the black botnet, and it was more than 100,000 by the certain date. With bot ID data, we can discover one more interesting thing. If we send the same MD5 hash to different CNC servers, they answer with the same bot ID. This means that they use a common database. Indeed, all visible CNC servers are just proxies that don't store any sensitive data. They connect to a backend server that is hidden deeply in the darknet, and you cannot find it actually. But we managed to find it, and this backend server also hosts the administrative panel that allows to control the botnet. This panel is a strong evidence that at least one remnant branch is controlled by Russian-speaking cyber criminals, as it uses Russian language, as you can see. The message with ID F0 may contain a list of commands for the bot to be executed. Server can ask a bot to download and run another malware, take a screenshot, or destroy the system. By tracking commands, we can get new malware samples and find out intentions of the bot masters. One of the most powerful features of Remnit is web injects. This is a screenshot of a real Japanese Yahoo login page. After entering username and a password, user should get into his account, and this how this page looks like on a computer infected with Remnit. In addition to username and password, it asks for bank card number, expiration date, and even CVC code. The same URL and even with the valid certificate, but the malware inserts a malicious script into the page. This script collects the data and sends it to cyber criminals. However, we can instantly get the source code of web injects and provide protections based on extracted artifacts, and also we can see targets of the malware. For example, in this screenshot you see that cyber criminals are interested in Pornhub users. Well, by infiltrating a botnet we managed to reveal its architecture, collect RSA signatures for IP addresses of CNC servers, assess botnet prevalence, and obtain web injects, malicious payloads used by Remit, and create protections for our customers. So, moving to our final goal, hijacking the botnet. We need to bring up a server that correctly implements malware communication protocol, make bots to connect it instead of the real CNC server. These servers should be perceived by bots as they are CNC servers so that we can control the bots. We have completed almost all preparation work. Now we only need to register some of DJ domains. There are 3 groups of bots with different RC4 encryption keys. We must choose the group of bots that we are going to control. And we must also choose RSA key for which we have collected the signature and acquired IP address. Then we need to find all DGA seeds for this subset of configurations and generate domain names for each seed. Obviously, some of them are already taken by cyber criminals and other researchers. We should register the ones closest to the top from the remaining and make them to resolve to our fake CNC server. That's it. Now we can receive connections from bots. I'm going to show a demo. For the demo I have chosen a sample that belongs to the currently running campaign domain 5. This sample requires server verification, so we need to use a collected RSA signature and the corresponding IP addresses. Here is a list of IP addresses. For that we collected signatures, and I changed the IP address of my virtual network card and set up the fake CNC server on my computer. I'm going to run the malware in a virtual machine. So, the demo. I'm running the malware in a virtual machine. It starts communication with our fake server. We see the authentication request and the response with the valid signature. The bot accepts the signature and sends the campaign name and computer information. Let's ask the bot to take a screenshot. The server sent the command, and we received the screenshot of the infected computer. Now I'm going to create a small script that will run Notepad on the infected system and write the text CPRCon 2020 in the Notepad window. I'm sending the command to the bot to download and execute my script. This is address of my local server. And the script has been executed. We see the message CPRCon 2020. Let's return to this picture. The part of the botnet doesn't require CNC server verification, so we don't need to have a signature and acquire a specific address. We just need to register domain names. We managed to register a very small part of domains for the bots that don't require server verification because all other domains are already taken. We can control only about 10% of the botnet, but this allowed us to gather some statistics. This chart shows how many bots run under different Windows versions, and most of infected computers run Windows 7. Amazing thing that Windows XP is still alive, and also Windows 10 is not affected by this version of Remnit. This chart shows bot survival over time. Assuming that initially 10,000 computers were infected, 6,000 will remain in a month and only 1,000 after 5 years. So 40% of computers are newly infected. And the summary for the bots without CNC server verification. 100,000 computers are currently infected with this old version that don't require verification. There are no CNC servers that currently control this part of the botnet. Most of bots run under Windows 7, and many computers infected with more than one malware. Almost 40% of this part of the botnet are newly infected computers, so takedown attempt will be useless. And the malware attacks outdated and unprotected systems. Windows 10 is not affected by this version, so it won't be a threat when everyone migrates to Windows 10. So don't use unprotected and outdated operating systems. That's it. Thank you.
Thank you very much to Alexey.